I'm Lucas.
And I'm Ryan.
And we're from Vassar College, and this is a project we did for our Bayesian statistics class last term. And the title is Towards a Bayesian Method to Estimate Future Realized Volatility. And just to give everyone kind of like a prelude to the stuff that we're talking about, like the finance-related stuff, we'll talk a bit about the options, like options terminology and volatility stuff. So options are a type of financial derivative that gives the owner the right but not the obligation to purchase or sell a security at a predetermined price on or before a certain date. And one of the main determinants of the price of options is the volatility of the underlying asset. And there's been multiple studies that have shown that implied volatility data is a better tool than historical volatility to estimate future volatility on the underlying asset. Most notably Latane and Rendelman, Kiros, and Manister and Beckers. Where implied volatility is basically the volatility that you can extract from the prices on the options. So in this project, we will investigate the use of a Bayesian method in order to yield a better estimate of future volatility than historical volatility of stocks without the use of implied volatility. And this method can be useful for stocks that have no existing options traded on them and where there therefore is no implied volatility data to refer to. And it's an extension on the work done by Ho et al. So for the data that we used, the underlying asset is the SPY, which is an ETF that is designed to track the S&P 500 index. And we'll be focusing on just the 30-day historical volatility. And the implied volatility data comes from the VIX, which is the CBOE Volatility Index, which is a measure of anticipated movements in the S&P 500, derived from the current traded prices of S&P 500 options. And the time frame for the data is November 1st, 2017 to April 10th, 2019. And so the main assumption when we're looking at the returns, or the log returns specifically, is that we assume that the daily log returns are normally distributed and centered at zero, which is a very common assumption to make when we're dealing with data like this. And this is in accordance to, for example, the work done by Carioli and Ho et al. And the difference with doing a frequentist method and the Bayesian method, which we're doing, is that in our normal model, we allow for the parameter values of the model to vary.
Yeah, so from allowing the parameter values to vary, we get the following likelihood distribution. Since our data is, we assume to be normally distributed, we get that all of our data points or returns at a given day I are normally distributed, which gives us the likelihood function for sigma. And then we assign three different prior distributions to sigma to see which distributions would produce the best implied volatility estimate. And for all of our priors, we're using weakly informative values to let the data drive the posterior results. So the first prior we chose was the inverse gamma prior. We chose this mainly because it's been proposed many times throughout the literature, such as by Carioli. So this is what the inverse gamma prior looks like. This is just a PDF of a gamma prior with weakly informative parameter values. And the next one we chose was a gamma prior. We chose this because in the work done by Ho et al., it has been shown to likely be a better prior distribution than the inverse gamma. And this is what a gamma prior looks like, once again, for weakly informative parameter values. And our final one we used was a truncated normal prior. And the main reason why we used a truncated normal is because the volatility or the variance of a distribution can be negative. So this is, in case you didn't know what a truncated normal prior looks like. And then to actually get our posterior results, we use this package called JAGS, or just another Gibbs sampler, where this package generates a Markov chain Monte Carlo to give you your posterior results. And what we specifically did was to try to get point estimates for each day in our data, we ran the JAGS package with the previous 30 days of the log returns, and then took samples from those Markov chains to then get our point estimate for each day. So here are an example of the diagnostics for the MCMC for a given day. In this case, it's the 3,330th day from our data set. And as you can see, the autocorrelation is low. It seems to be mixing fairly well. The only point that might be an issue is that it doesn't seem, we don't have very long chain, so it would be hard to assume convergence, but we ended up running one of the chains for significantly longer so that we could try to see if by this point it had converged, and we saw that it did in fact converge by this point.
Okay, so for all of our estimation values that we got, we used the following method to estimate or to get the estimation error, the same method as Ho et al. Used. And so, well, it's the following method, and where sigma BI is the Bayesian volatility estimate from our model, and sigma II is the implied volatility, and sigma HI is the historic volatility for each day. And here's the results that we got for a few days, and we can see the results from the inverse gamma model, the truncated normal model, and then we also show the historical error. And as we can see, the inverse gamma model didn't perform that well, whereas the gamma and the truncated normal prior models performed very, very similarly up to 3 decimal points. And they actually produce a somewhat better or smaller error than the historical error. So in conclusion, this project investigates if a Bayesian method could estimate, or a Bayesian estimate of realized volatility gives a better estimate of implied volatility than the realized volatility itself. And our results produced a 6.29% improvement using both the gamma and the truncated normal prior. And as we can see, the results produced by the typical choice of the inverse gamma prior are significantly worse than that produced by the gamma and the truncated normal priors, which is kind of interesting since it's very commonly used. So one of the major errors with the model that we use, also we assume that the data is normally distributed, which is not really the case, and we can see that in the following slide, we did a Shapiro-Wilk test, which is a common test that tests if the distribution is normal or not. And as we can see, it fails the Shapiro-Wilk test. So one solution to this is to have a different distribution for the data. And one distribution that has been shown to perform pretty well is what's called the Solis distribution, as you can see here, which is the distribution that converges to the Gaussian or the normal distribution when the parameter value Q equals 1. So we can see here that it clearly provides a better fit to log returns than just a normal distribution. And yes, that's the project.
Great, thanks so much. All right, so we have a couple of questions from the audience. First, one person asked, was there anything surprising about the results that you found? Was there anything where you were, taken by surprise?
Yeah, definitely because we had seen that the inverse gamma prior for a model like this would produce worse results than, well, specifically the gamma prior, but it was way worse than we thought it would be. So that was kind of surprising, like the extent to which how bad it actually performed.
Yeah. So you mentioned that you took this as part of a Bayesian statistics course. So someone asked, do you consider yourselves Bayesians now?
I don't know if we can fully claim that title, but definitely more understanding of the methods, and I definitely think about things a lot more in a Bayesian context and a frequentist context as my first thought, but I don't know if I can go quite fully to that extent at this point.
Yeah, sure. That's a nice answer. You're partially Bayesian. Okay. So, Last question that someone asked was just if you could talk a little bit about what you think the broader impacts of your results are.
I think it's difficult to say at this point. The project isn't really that full covering at this point, so I think that it still needs some more work. Like, for example, exploring other distributions, because right now the improvement of the model isn't really that significant. But it stands to see if one could use a model like this, like a Bayesian model like this, tweaking the data model or maybe some other prior choices and actually yield better results. So it's, I guess we'll see.
Yeah. All right. We'll stay tuned then. All right. Thanks so much, you two.
Thank you.
Thank you.